So I just want to remark now that we're at a stage where we could actually give a probabilistic version of theorem 1.10 of IUT4. So when I say probabilistic version, it's kind of like it's actually a simpler version because of because some of the inequalities I'm using are not quite as sharp as they are in IUT4. But I think it's kind of more it's easier to see what's going on. So here's the statement. The statement is the following. So here's the theorem. So this is from so assuming corollary 3.12 of IUT3. So that main inequality. So we get the following. We have that minus degree here, f naught of PQ is less than or equal to, well, the whole of the theta pilot object. We can write it as the sum over P, including the infinite place, of EP squared of this natural log of R VU. Okay. So let's do it like this. R0, 1, so I don't like how that was written. Let's do it like this. 0. So now you can see the J's vary as well. Okay, so this is the kind of probabilistic version of what we have here. And so this is the result of the log volume computation. And the computation of the whole of, so this is kind of an upper bound for the whole of the multi-radial representation of the theta pilot object. Okay, and so here you can actually write out what this thing does. So there's a bunch of terms, right? So here, so locally, we have that here E P squared of, okay, now this gets long, right? But what we get is that there's this minus here. So there's this thing. I think we call this the first term. Then there's the different term, right? Sorry, this is the different. Let me clean this up a little bit. So there's J and then there. So that we have 1 minus the biggest one. Okay. This is all multiplied by the natural log of P. Then we add this term that comes from ramification. Okay, here, let's say, let's do it like this. Ram here. Okay, and then we'll have 1 plus J plus 1 natural log of some constant that depends on P. Okay, and plus one more term, which is this, let's write it down here. This expectation of the sum, 0 to J, of the natural log of E over P, like so. Okay, so the sum of the inertia degrees, and all right. So let's get rid of this one. Where is it? Here. Okay, and let me circle it. Okay, so we have this thing here. To kind of give. Okay, so this is what we have. We have, you know, we can compute each part of these. So let me say a couple words about this. So this part here can be. So I guess these two parts here. So this can be improved a little from IUT3, and then this part here. So this is what turns into the theta pilot degree. All right, and and then this will turn into some sort of like averaged different. This turns into some sort of averaged averaged ramification degree. Okay, and to remind you that this thing there's two averages. First over with fixed j, and we vary over these elements of v underline p to the j plus 1. So the lifts of p to the field k in that prescribed form, and it's the averages taken with these weird weights. And then there's this kind of precession averaging, which is the averages over j. Okay, so there's two averages going on. Okay, and so this probabilistic version is something that I'll work out now to get a form of Szpiro. Okay. So what we want to do is we want to break the log volume computation down. So we want to compute. So what we'll do is so we want to compute here. Here the expectation. So this is this thing varies over tuples. Okay, so now we're doing a particular case. So here L, so L is L, this thing here, and this is going to be a product here. So of j plus 1 j plus 1 p-adic fields. There are completions at these lifts. Okay, and then the weights of this thing are weird. So now we'll do log mu L like this of here. Now we're going to take the disk in this, the poly disk in here, 0, and then the radius here we'll call this R. Like so. Let's do it like that. Okay, so this is what we want to compute. We want to compute this thing, where our radius is this here. So here the radius so this is going to be so should we do it in terms of logs? Let's do logs. Natural log of this thing. Okay, so the natural log of the radius is going to be minus. So we had a plus here. Let's see. Yeah. So this thing. So sorry. This is it is going to be a minus or p q double underline here. Minus beta. This is well defined. So this thing here, so this is going to be here. This thing's actually diff. So we'll do that. This vector here. Let's write it like this. Oh. So we'll take this thing, 1 infinity, so we subtract the maximum. And then we have plus, so there's going to be, I guess, 3 terms, plus j plus 1. Then we're going to have natural log ln, and let's call this BP, where BP, here, let's kind of define this. Oh, let me just keep moving on. Plus the sum from I is equal to 0 up to j of natural log of e, the ramification indices here. Okay, so we have these 3 terms here. All right, so that's what we have. This is the difference for each of the fields. So maybe I didn't say this. So this is going to be the different here of V0 over P all the way to the different of Vj over P, like so. And what else was I going to say? Oh yeah, that's equal to this, where this is equal to that. Okay, and this is the radius that we're interested in here. So there's a small correction that needs to be made here. This term needs to be multiplied by log p. It turns out so that log, I mean, this is kind of a general thing here. If I just fix some radius here, and I were going to take this thing, so this is just equal to the natural log. So less than or equal to the natural log of the radius, like so. That's it. So this is a formula that we have that we're going to apply. So this is a formula we need. I'll link to a proof of this if I make a video of it in the description. And then okay, and so this tells us that this expectation of here of the measures of these polydiscs okay, so this is going to be equal to so this is of course equal to the expected value of the I guess the natural log of our VU, and so then this is going to be equal to the expectation of the 3 terms. So this is the expectation of the first term. I guess second term, plus the expectation of the third term. Okay, and so let's just kind of, so again, this is the first term, this is the second term, this is the third term. I guess we could actually, well, do I want to break this up a little bit more? Okay, so let me just say the first term. Yeah, maybe we can break this up a little bit more. So the first term only appears when there is ramification. Same with the second term. So the second term only appears if one of the V's are going to be ramified, and same with the last term. So they all have to appear when one of them is ramified. This term only appears when it's bad, and then otherwise we'll set this thing equal to 1. So yeah. So let me just kind of maybe we can write it out as more than let's call it plus the fourth term. Let's do fourth term. Okay, and so we'll just go like that. So all right, and then I'll just compute each one of those. So let's break down that first bit. So we were looking at this minus here. This double underline here, minus, then we had minus this different, like so. And then, okay, so we had, this is one of the terms. And so this thing is, I guess this is less than or equal to minus, like this. So this is the jth term. J squared plus this term here. Minus, let's see, so I guess this one minus plus this maximum term, and then plus 1. Okay, so again, this term only appears, so this term only appears when it's ramified, and this term only appears when it's bad. Okay, so we need some ramification for this to occur. All right, so so the first term, so the e of the first term, so this is the expectation of I guess we can say minus the expectation ord p here of this thing. Oh, okay, and then e of the second term, the expectation of the second term. So this is the expected difference, or I guess minus the expected difference of this guy. So I guess this is already a minus minus. So sorry, this should be plus, and this should be minus minus minus, and then this should be minus. Okay, so okay, I'm just going to omit that. Diff. So this is plus minus here, like so, and then plus e. I guess so. Then we could take care of this term, e of this extra term. Okay, so we have to compute each one of those. So this is the expectation that, and so this only appears when there's a ramified vector here. So let's call this ram here. And so this thing this is equal to 1 if so v I is ramified for some I. Let's do it like this. I'm sorry, not like that. In this vector, this thing is v0 up to vj, and then it's going to be 0 otherwise. So if all of these things in the vector are ramified, then we call the tuple unramified. Okay, so we have this first, second, and extra term. I guess we have plus this extra term. All right.